everyone. My name is Mayank. I'm a security researcher. I work for this company called Stealth Security. And today I'll be talking about how to break fraud and bot detection solutions. So a bit of motivation and background for this talk. Online fraud is a pretty big problem, like ever since the beginning of the internet. People have poured in a whole, like millions and billions of dollars to solve this particular problem. Like even a couple of days ago, one of the fraud detection companies got acquired for more than $800 million. So this is a big problem. Bot detection is another emerging problem where companies are trying to defend against automated programs. They could be, for example, scraping their websites, or they would be launching other automated attacks. So more than a year ago, I started looking at some of the implementations of these fraud and bot detection solutions, and I found certain security issues. Once I looked at multiple of these solutions, certain common security issues or common security attacks, they emerged. So this talk is culmination of common security issues which I found with multiple fraud and bot detection solutions which are deployed in the real world. So let's go over the agenda for this talk. First of all, I'll go over some of the architectural overviews of many of these solutions. So one thing to mention is that these solutions are not only vendors. There are actually in-house fraud and bot detection solutions, like giant banking websites. They have built their own solutions as well. So first of all, I'll go over some of the common architectures which I see, which are deployed in the real world. Then I will go over the threat model. So in the threat model, I will introduce what are the exact goals of the attacker in this particular scenario, what the attacker is trying to achieve, and then exactly what are the capabilities of the attacker in this game. So once I've defined the threat model, and once I've defined the common architectures we see in the real world, I'll talk about the security issues which arrive given these scenarios. And I'll talk about common security attacks which work against many of these solutions. Then at the end, I'll talk about some of the takeaways. All right, so let's start off with defining the problems. So fraud detection, as many of you know, is basically you're trying to defend against fraudulent activities. So these could be fraudulent logins, they could be fraudulent payments. For example, if you think of like a banking application, you might be looking for fraudulent logins. So, for example, a bank account is extremely high value. So even though you have your normal username and password as the authentication measure, banks are looking for even more interesting scenarios to detect account takeovers. For example, if suppose every time I log in to my banking account, I will log in from San Francisco, and certainly there is a login attempt from, say, an IP address in LA or in Israel, then it's potentially suspicious. So it might, for example, trigger the fraud detection solution. Like for example, for payments, like for credit card payments, if there are any fraudulent or any suspicious activities on your credit cards, it would trigger, for example, the fraud detection solution. And then one thing to mention is that usually the fraud detection solutions, they're looking for anomalies, and usually they're looking for anomalies for a particular user. Like as I mentioned, if for example I always log in from an IP in San Francisco, and there is an anomalous activity, like given my past behavioral history of me logging in from only that particular region, if something completely new happens or something suspicious happens, these are the kind of activities which trigger these kind of anomaly detection systems. So for this talk, I'll mostly focus on fraud detection solutions which are focused on authentication. So they're looking for fraudulent logins. So another related problem is bot detection, where what you're trying to do is you're trying to defend against bots. So these are automated programs which could be launching different kind of attacks. For example, they could be launching account takeover attacks. So in this scenario, so in case of a fraud detection solution, you can assume that, for example, there is a malware or something, and the attacker is able to get the credentials of the user. So they're again using the same credentials to log in, but there might be something suspicious about the login event. For bot detection, what happens is, suppose there is a scenario in which a particular company gets compromised. say for example, LinkedIn got compromised, and their credentials are publicly leaked online, right? So the next step, what LinkedIn would do is they would ask their users to reset the password. But what happens is people reuse their passwords across different websites. So what the bad guys do is they take an advantage of this scenario where they actually test these lead credentials across different websites. For example, a particular user, they may have the same credential for their LinkedIn account and their banking application. And then when LinkedIn, for example, got compromised, LinkedIn asked them to reset the password for LinkedIn. But LinkedIn has no idea where they are reusing the same password. So the user may not reset the password on the banking application or another website. So what these bad guys are doing is basically they are writing these automated programs which would take in these inputs, these giant credential dumps, and then what they would do is they would launch these against different websites. So for example, some banking application, and they would try to see how many of these credentials actually also work against this other website, right? So in this scenario, basically your authentication is at risk, where the requests coming in, they may not be necessarily fraudulent, but there would be so many requests coming in that you want to differentiate and you want to also protect your users from these sort of bots. So that's one scenario. Another scenario is, for example, scraping. Again, going back to LinkedIn, for example, LinkedIn has professional profiles of a lot of users, right? And that's their critical piece of data. They want to protect this data. But there could be other bad guys who would be writing programs to automatically scrape this information, right? So again, they want to protect against this sort of scraping attacks. And one thing to mention that, again, bot detection is also, I would say, another machine learning / anomaly detection problem, where usually what these bot detection solutions are trying to do is they're trying to look for anomalies across entire populations of users or across time periods. For example, like for authentication problem, like if you only see, say, 10,000 login requests per minute, and then suddenly there is a large spike in the number of authentication requests, this could be an indicator of there could be some sort of an attack going on, where somebody's writing a bot to test authentication. Or for example, like if you see there is a large spike in the number of pages which are fetched by a particular user session, again, that could be anomalous. So again, this is kind of like an anomaly detection problem. So now, since I have defined these problems, let's go over how these solutions are actually deployed in the real world. So this is an architectural diagram of like one of the common deployment models of some of these solutions. So what you have is on the right side, you have your web server. So think of it as a banking application, right? And on the left side, you have your client browser, which is trying to authenticate to the banking application. So what happens is in the first, and you have the service provider, which is basically the fraud detection solution or the bot detection solution, right? So what happens is in the first step, the client browser fetches the authentication page, the login page from the web server. And what happens is in the authentication page, there is a script tag which basically gets this fingerprint.js file, which is embedded, which is basically fetched from the service provider, from the cloud. Say it's located at some other, say abc.com/fingerprint.js. So this is the magical JavaScript file, which what it tries to do is it tries to create a unique fingerprint of your browser, basically of your machine, as well as of the user itself. So how the user interacts with the website, right? So as you can see, the third step is basically this fingerprint is then sent back to the cloud, to the service provider. And then within the cloud, there could be like different machine learning models, which could be analyzing these fingerprints. So you can use this analysis in multiple ways. For example, what you can do is you could look for like discrepancies within the fingerprint itself. Like there is something unique about this fingerprint. Or for example, if you are trying to compare this fingerprint across entire population of users, like this fingerprint is very unique. I've never seen a user log in with this kind of fingerprint. Or for example, in case of a fraud detection solution, what you might have done is you might have created a fingerprint profile of your user. So usually this user always logs in from this kind of browser. So this is the kind of fingerprint. And then suddenly you see completely different fingerprint. Even though the username and password are correct, it could be potentially fraudulent, right? So this would, for example, trigger the fraud detection solution. So the next step is basically you submit the form. You type username and password, it's sent to the web server. Then the fifth step is basically the web server talks to the service provider, and then if, for example, they talk to each other and there is exchange of some information. Usually they are asked for some sort of a risk score. Like, given this authentication session, what do you think about this session? Like, is it fraudulent or not? Is it a bot activity or is it a human activity, right? So this risk score is exchanged from the service provider. And then usually there is some sort of a policy. So think about this risk score, for example, as like a probability value from a number from 0 to 1, right? With a higher number being indicative of fraud. So you could define like a policy that if the risk score is more than 0.8, then for example, I want to go ahead and block this. So that comes to the mitigator, which is basically some sort of inline device, or it could be the web server itself, which basically analyzes the risk score, and based on the policy, it might allow the request to go through, or it might block it. So this is like a common architecture, both for fraud detection solutions and bot detection solutions. There is another variant of these sort of deployments where what happens is there is some sort of an inline deployment model where what happens is you have the client browser on one side, again you have the web server, but instead of the cloud, there is some sort of an inline device which sits between the client browser and the web server, right? So it could be just in front of the web server, it could be like at the CDN level, so there are multiple variants, but this is the overall idea. So in this case, what happens is, like once you fetch the web page, the inline device which sits in the middle, it injects this fingerprint.js file automatically. So in the previous scenario, you actually had to change the web application, and you would have to insert the script tag that from basically load the JavaScript file from the cloud provider. So you had to basically change the application a little bit. In this scenario, the application developer has no idea what's going on. The inline device basically automatically injects this JavaScript in the page, right? So this fingerprint.js file is then sent back to the client browser. It, again, the magical file executes, gets this magical fingerprint, which is then sent back. And then since it's an inline device, it can automatically either block it or allow it, right? So again, same sort of deployment model you can see for both fraud and bot detection solutions. So now I've explained like what is the problem and how these solutions are deployed in the real world. Let's talk about the attacker. So let's talk about the threat model. So what is the goal of the attacker? So in case of bot detection solutions, what the attacker goal is, for example, if you go back to LinkedIn scraping example, they want to launch these kind of attacks without getting blocked, right? For example, LinkedIn might be blocking their IP address or something very specific, right? But they want to launch a high volume of this attack without getting blocked or without spending a lot of money, like spinning up a lot of AWS instances or whatever, right? For a fraud detection solution, let's assume that, again, for authentication, the attacker has the authentication, the credentials, but they know that if they test, there is a fraud detection solution deployed. So if they use any random browser and they try to authenticate using those same credentials, it might trigger this fraud detection solution. So in this case, they want to authenticate and get the money from the account without triggering the fraud detection solution. So this is the attacker goal. And then the threat model is basically, we assume, again here, is the attacker has full control over the browser. So the left side, which you see, the client browser, the attacker has full control of the browser, they have full control of the machine, right? Which is makes sense, for example, for bot detection solution. For launching like a scraping attack, of course, they control the infrastructure. And for, again, for logging in and bypassing a fraud detection solution, of course, they control the browser, they can authenticate, right? So as a consequence of that, the attacker can basically craft any HTTP request they want to the web server, and they can modify any response coming back from the web server or any response originating from the browser to the web server, right? They basically control the network on the client side, right? So now, given these attacker capabilities and given the architecture which I have just described, now let's talk about the fundamental issues, or the issues which originate from this sort of an architecture. So the first problem with these kind of scenarios and these kind of deployments is the attacker can reverse engineer the entire sensor. So the sensor is basically this magical JavaScript file which is sent to your browser, right? but I, as an attacker, control the browser, so I can see exactly what's inside the JavaScript file, right? So let's talk about what is in this JavaScript file. What is in this magical JavaScript file? What kind of things it's collecting? So the first thing is the browser fingerprint. The browser fingerprint, as many of you know, is basically you're trying to create a somewhat unique fingerprint of your browser/device, right? So there are certain unique quirks about your browser, which make it unique, or which make it semi-unique among the entire population of browsers, right? And then there is actually a lot of work which has been done on browser fingerprinting, especially in terms of from the perspective of user tracking. So there are a lot of scripts available online where what they try to do is they try to create a unique fingerprint of the browser of the user, and then they try to track the same user across different websites using the same browser fingerprint. So these fraud and bot detection solutions are using the similar concept, but for dealing with these problems. So let's take this example. So this is actually from a website called panopticlick.eff. So EFF actually did this study where they were trying to understand how unique is a browser fingerprint, or how much value can you extract from a browser fingerprint. So what happens is basically you send down this JavaScript snippet, and what it does is it queries different parameters of your browser, or different properties of your browser, which may reveal some information about your browser, which might be semi-unique. Like for example, the first column is basically the browser characteristic, which is, for example, the kind of thing that you're looking at. For example, you can see, for example, you can, like one of these is the system fonts. So what this JavaScript file is looking for is the list of system fonts installed on that particular browser. So give me a list of all the fonts which are installed on that machine, right? So if you install any unique font, any font, like if you are, for example, a UI developer, you're playing around with a bunch of fonts, you install a bunch of fonts on a machine, that makes a machine identifiable very quickly, right? Like on the right hand side, the value is basically all the list of fonts which are installed on that machine. The third column is again interesting. So if you look at system fonts, the third column is like 1 in X browsers have this value. So 1 in 24 browsers in the entire population of their data set had the same set of fonts installed as this browser. So this is a test browser I was using, right? So basically, given the entire population or the entire data set, I think their data set is probably around 1.5 million browser fingerprints right now, or probably more than that. So given this entire data set, 1 in 24 browsers will have exactly the same kind of fonts installed as my browser, right? And then what you want to do is you want to aggregate these kind of pieces of information to create some sort of a unique fingerprint of your browser. Like for example, I was meddling around, so I was using some weird version of Chromium. So if you look at the user agent string, which is the from the third item from the bottom, so the user agent string, my user agent string is more than like 1 in more than a million browsers have exactly the same user agent string as my browser, right? Which makes it very, very unique and very fingerprintable. And then the second column is the bits of identifying information, which is basically the log of that 1 million number to the base 2. Like these are how many bits of information you can extract. So the idea is that in an ideal world, suppose the population right now is say 10 billion people, right? And every browser has a unique fingerprint. So all you need is a log of 10 billion to the base 2 bits of information. Like if you can extract these many bits of information from the browser fingerprint, you can uniquely basically fingerprint every browser. But according to most of the studies, you don't have these many bits of information. Like if you could do that, you can use it for authentication, for example. But right now we are not at that stage. And actually there is a lot of work which is going on to defeat browser fingerprinting. Because again, as I mentioned, it's used for user tracking as well. Okay, so here is a small list of things which these scripts are looking for to create this browser fingerprint. So I'll go over some of these pretty quickly. First of all, they're trying to fingerprint the hardware. For example, they can ask like, what is the CPU architecture? How much memory is available on this device, right? Another interesting one is the GPU canvas fingerprint, which came out a few years ago, made a lot of news, which is pretty interesting. So the idea is they're trying to fingerprint your GPU unit. So what they do is they use something called this HTML5 canvas element, and then they draw, for example, they draw some sort of image on that canvas element, right? Or they write some sort of text on that canvas element. And then what they do next is they try to read the raw pixels from that canvas element back, right? And then because of some changes in how the GPUs are implemented, and even because of differences in the GPU drivers, when you read the raw pixels back from this canvas element, the results are slightly different, right? So people are basically using this to fingerprint your GPU, right? Another interesting one which came out recently, sometime last year, was very cool, was audio stack fingerprinting, where what these guys are trying to do is they're trying to fingerprint your audio stack, like your audio card. So the way it works is basically what they try to do is they try to play some sort of a signal, for example, a sinusoidal signal on your machine. Of course, the volume is 0, so of course you don't hear anything. And then they use some sort of an audio context element, something similar like a canvas element, which uses like fast Fourier transformation. I'm not an expert at signal processing, but they do some sort of manipulation with signals, and then they read it back. And similar like with canvas fingerprinting, when you read back this audio signal, there are certain changes because of how your audio card is installed, like what is the hardware, or also what is the device driver version of that card. And then you can identify basically bits of information from your audio card. So that was pretty cool. The most interesting part is, so this actually wasn't, I think it came from an academic paper. And as soon as the paper was published, some of the fraud detection solutions, they basically implemented the same thing within a week or two, which was fascinating, which kind of shows that these guys are trying to extract as much information as possible from the browser, right? And then there are the normal things. For example, they're looking at the user agent string, how unique is your user agent. They're looking at the operating system version. They're looking at your display, like what is the screen size, what is the color depth. They're looking at browser customizations, like as I mentioned, like they're looking at a list of fonts installed on your machine. They're looking at a list of plugins, browser extensions installed on a browser. So again, the more browser extensions you install, the more unique browser extensions you install, the more unique your browser becomes, so they can track you in an easier way, right? They're looking for example, what is the time zone, what are the list of language packs installed on a browser, right? All of these are accessible from JavaScript, which makes it very interesting, right? And then I also noticed like many of these solutions, they are also doing some weird manipulations with JavaScript. For example, they would do some weird floating point calculation. And the idea is basically to try to figure out if it's an actual browser or not, because if it's not an actual browser, again, you won't get a result back of this calculation, right? Another thing would be maybe they're trying to fingerprint how long it takes to do some sort of calculations. I'm not exactly sure. It was interesting. Another thing I see is many of them, they do some sort of weird manipulations with the DOM structure. So they would add some items to the DOM, or they would remove them. They would add like event listeners to them. So again, the idea is to figure out basically, yeah, are you running an actual browser or not, right? And then there is actually a lot of work done. Like for example, this is an open source library called Fingerprint JS2. So this is the output of the same browser I was using, right? So you can see these are the different components of the browser fingerprint. And on top of that, basically what it's doing is it's calculating the entire MD5 of the entire browser fingerprint. So it basically appends, it creates this long string, then basically it calculates the MD5, and then that's the unique or semi-unique fingerprint of my particular browser. So the reason to show this is basically like these fraud and bot detection solutions, they are using browser fingerprinting, but it's not like something which is out of the world, because a lot of these techniques are available in open source solutions. There's another project called PinLady, which basically you can generate a JavaScript custom for you, which can fingerprint browser extensions, for example. So yeah, like this code is available, and I used this, for example, this project to show some a proof of concept attacks. So yeah, next step is they create this unique fingerprint of your browser or / your device. Now what they also want to do is they want to create the fingerprint of you as the user, right? To be more specific of the user behavior. So the way they do this is basically, again, kind of sounds very intrusive, but they're trying to build a picture of how are you interacting with the web page, right? So how do you, for example, move your mouse? Like what is your typing speed? How fast do you move your mouse? And so forth. So what they do is basically they use like add event listeners. So they attach a bunch of event listeners to a bunch of events. For example, key press. Like whenever there is a key press, it would call this listener, right? So it would record that this key was pressed at this particular time, right? For mouse, for example, you could add event listeners for mouse movement, for mouse clicks, and so forth. They have like event listeners for touchpad. Like if you're using a browser on your iPad, if you touch a particular point, they could record the coordinates of where it was touched on that device, right? Another very interesting one is basically if you're running the browser again on your iPad or on your phone, they can use the device accelerometer. So using that, you can actually query the three-dimensional angle of your device. Like right now, I'm holding my device at this particular angle, right? So you can record even the changes in the speed of your device, or you can record even the movements of the device, which is again pretty interesting. And then I think some of these solutions they do employ it. And then what they do is they also record timing information of when this event got fired. So the idea is basically you want to basically create this entire picture. Like for example, I loaded this authentication page. First thing I did at time equals t equals 1 is I moved my mouse from this coordinate to this coordinate. Then at time t equals 2, I clicked the mouse at this coordinate. And then time t equals 3, I had a bunch of these key presses, which might be, for example, I'm typing my username and password. Time t equals 5, what I did was I clicked this button. Might be the submit page, right? A submit button, and then this entire payload is sent back. So on the server side, basically, you can recreate this entire user session just by looking at this user behavior fingerprint. The next step is basically anti-tampering and anti-reversing. Again, as I mentioned, this is this magical JavaScript file which is sent back to your browser. Again, they're querying and they're extracting all these pieces of information which is sent back to the cloud, and which is again consumed by machine learning models, right? So these are basically your inputs to your machine learning models. And then, of course, these guys, they want to protect this JavaScript snippet. So I see a lot of JavaScript obfuscation is pretty common. So they are trying to obfuscate the code, so it's harder to read and harder to figure out exactly what they're doing. For example, in one particular scenario, I've seen they were using, so they were using packing. So they were using XOR based packing, where they would send down the code, which is packed, and they would send this giant XOR, this array of integers, and they would XOR the code to basically get back the actual code, right? In many scenarios, I saw them, they were randomizing the location from where the JavaScript file would be loaded. They were even randomizing the source code of the page, of the JavaScript snippet, which was interesting. So they were employing a whole bunch of anti-tampering and anti-reversing techniques, but yeah, given enough time, basically you can basically bypass most of them. And then the final step is basically once this snippet calculates the browser fingerprint and the user fingerprint, it creates this payload. So this can be like a long string of all these events and this browser fingerprint, and then basically it's sent back to the cloud. So usually they are using some sort of an encoding scheme. Like base64 I've found to be very common. Many of these solutions, they were using encryption. Like I saw like one of the solutions was using symmetric encryption, DES, and the key was actually in the JavaScript snippet. So I don't know what they were trying to do. Maybe it was security by obscurity. But again, since I can see the JavaScript file, I mean, I have the key, right? And I saw like in some scenarios, they were actually implementing their custom encryption schemes, which is usually not recommended, especially if you talk to cryptographers. And I didn't think that they were especially very strong or very sophisticated. So this is the entire picture of what actually happens in your browser and what they're trying to calculate. Again, this is again sent back to the cloud. They do some magic with ML, right? So this is basically the first step. Like I, as an attacker, can see exactly what this solution is trying to do. Right? These are the kind of things they're collecting from my browser. Okay, now let's talk about the next problem. So the next problem is there are no guarantees of the correct execution of JavaScript. So basically, this solution, this fraud/bot detection solution, it sent down the JavaScript file to the client, and they assume that this would run in a normal browser. They would calculate, they would gather all these fingerprints, which would be analyzed in the cloud, right? But actually, there are no guarantees because going back to our threat model, I, as an attacker, I control the browser, I control that machine, right? For example, the first example is the headless browsers, right? So headless browsers are browsers without a GUI. They're often used for automation and testing. And then many times they are full browsers, or many times you are actually running JavaScript in a virtual DOM. And then, of course, they are scriptable. For example, you can inject events, like you can inject, like you should go and to this button and click this button, or you can inject key streams or whatever, right? And there are a whole bunch of them. Like most recently, even Chrome released their headless browser. There is Phantom.js, there is Slimmer.js, a whole bunch of them. And the idea is that, yeah, you can use these browsers to basically automate your requests. And I found that many of the bot and fraud detection solutions, which were especially built in-house by bigger companies, like this alone was enough to basically bypass them or run past them, where maybe they were not very well maintained, or they were not looking for these sort of solutions. But yeah, this was pretty effective against some of the solutions which were deployed. Interestingly, there are more sophisticated solutions, especially coming from vendors, which were specifically looking for headless browsers, but they were looking for headless browsers using JavaScript. So you could actually see exactly how they are looking for these browsers. And again, you could find ways to bypass them as well. So which was kind of interesting. So there is always this arms race. So the next problem is what I would call as the stripping attack, which was very interesting. I don't know, it was surprising. So going back to the architecture, like as I mentioned, there's the service provider which is in the cloud, and then there's this magical JavaScript fingerprint.js file which is fetched, right? And it sends this fingerprint back to the cloud, which analyzes it, and then the web server gets this risk score. What if you never load this JavaScript file? And what if you never send this fingerprint back to the cloud? Like, what happens? Interestingly, in many scenarios, this was enough to bypass some of the solutions. And I think the reason was what the solution, like either the web server, they were not fully confident in the service provider. Like they would ask, like, what do you know about this particular session? And and the service provider would say, which session? I haven't seen this session. And maybe some of the solutions they fail open, so they would allow these requests to go through. Because if you block a legitimate request, you are impacting your business, right? So in many cases, again, this was enough to basically bypass some of these solutions. And interestingly, some of these vendors, they actually realized that this is a problem, so they would implement. So in one particular case, they would implement a defense against this. So what they would do is, in the normal page, in the normal login page, they would check if fingerprint.js file was loaded or not. And if the file was not loaded, they would not load the entire page. So it would actually never load the entire page. But again, this check was again done on the client side. So what I did, for example, was I mapped for example, the service provider was abc.com. I mapped it to localhost. And then I had fingerprint.js file on my localhost, which was an empty file, right? So when they did the check failed. The check passed, sorry, right? So yeah, that was enough to basically bypass that particular vendor, for example. And then surprisingly, this also worked in the other scenario, where actually there was an inline device, where basically what I did was I used a man-in-the-middle proxy, which sat in front of my client browser, and it would basically strip out this JavaScript file. And then surprisingly, in some of these cases, this was enough. Again, I think the reason is basically the web server, or for example, the banking application in this scenario, they are worried that if you block legitimate requests, it might be bad for their business. So in this case, what I did was I used a man-in-the-middle proxy. Either I would rewrite the page before it hits my browser, or what I would do is I would modify the payload when it's going back from my browser to the web server. So this was the stripping attack. Again, so many of these solutions, of course, they don't fall for this sort of a dumb attack. So they have checks like, if you don't see the fingerprint, let's not allow this request to go through. But then the next problem is replay attacks. So the idea is that, for example, this is like a proof of concept. So I was running example.com is basically my local host. I have like an authentication page, login.php, and then you have this user equals, which is the username, and then there's the password equals field, which is the password, right? And then after that, there is this giant red box, which is fingerprint equals something. So basically, I use the fingerprint.js open source library, and then I'm calculating a subset of my browser fingerprint, and I'm sending it back to the server, right? So basically, I'm mimicking like what kind of requests happen in the real world. So the problem with this scenario, or this fingerprint, is if you look at this fingerprint equals string, there is no token in this string, which is dynamic. So what happens is, if I can capture a browser fingerprint, for example, I am a legitimate user, I'm using the same website, I capture my browser fingerprint, right? And I capture it. And if it's not dynamic, I can basically replay the same fingerprint again and again, right? So I don't actually have to run the JavaScript file in the browser. I can just replay the same browser fingerprint again and again. For example, in this case, what I did was I have this bash script, which is basically an infinite loop, which is basically sending the same username and password and the browser fingerprint to the web server, right? So in case of a real attack, instead of sending the same username and password and the browser fingerprint, the attacker, what they would do is they would change the username and password and would keep the fingerprint the same. Or they would, for example, modify the fingerprint slightly, right? So in this case, there is no check on the freshness of the payload, right? So you could replay the same thing again and again. So the solution for replay attacks is you should introduce some sort of a token which is dynamic. So every time you actually send the page, send the JavaScript file, there's some sort of a token which is unique for that session. And then actually I found like some of the guys who were implementing this, they didn't implement it correctly. So in one scenario, what I found was there was this bot detection solution. What they were doing was they were introducing a dynamic random token inside the payload. And the way they were doing it was they would get the timestamp of when the JavaScript ran. They would get the browser fingerprint. So what they would do is they would append the timestamp in front of the browser fingerprint. And then they had a function, some function f, which would take the timestamp as an input and would generate a token, which was basically the function of that timestamp, right? But again, the problem was this function f was in JavaScript. So again, I as an attacker know exactly what you're doing or how you're calculating this token. And I can replicate the same logic in Python or in Bash or whatever, right? So for example, this was enough to bypass this particular solution. And basically, I as an attacker, I can pick any timestamp I want. And because of this function, I would get the corresponding token, right? So it would basically bypass some of these checks. The correct way to do this is basically to use some sort of scenario, like for example, CSRF tokens, where every time you get the page, you get some sort of a dynamic token, which gets changed. So every time you send the payload, you basically, you can check if the token is correct or not, right? But again, this is very hard to implement, especially for solutions which are implemented in the cloud. Like for inline solutions, since they sit in front of the web server, they can dynamically change the page. They can dynamically inject the tokens. But I'm not sure exactly how you would do that in some sort of a cloud-based deployment. Okay, so now let's talk about the next problem. So first biggest problem was basically I as an attacker know exactly what they're collecting from my browser. So I know what they're looking for. Second big problem is basically there are no guarantees that once they send the JavaScript, it will actually execute in the browser, in a real browser. The third problem is that even if the JavaScript executes, there are no guarantees of, like, if you get the browser fingerprint back, it is actually legitimate, or actually it is correct. Because what they're doing is basically they're calculating this browser fingerprint. And the way they calculate this browser fingerprint is, for example, they query certain characteristics of the browser. For example, if they want to figure out what is my CPU architecture, what they would do is they would call this navigator.cpu class, right? It will return if I'm running on x86 or ARM or whatever, right? But since I control the browser, I can lie back to this function call, right? Which basically brings us to the next topic of forging browser fingerprints, where basically you are basically lying back to this JavaScript file. So the browser actually lies back to the JavaScript file. So there is actually some work done on this, so there's this paper called FP Random, which came out a few months ago, when I was already doing some of this work. What they did was these guys implemented a custom browser, which would introduce some noise whenever somebody was calculating the browser fingerprint, right? For example, for the canvas fingerprint, when you write something on the canvas and you're trying to read it back, and you're trying to read the raw pixels back, in this function, they would introduce some sort of noise. So the idea is basically, because of this noise, the fingerprint would change. And the reason they were trying to do this was because to basically block user tracking. So that was their main idea. But again, you can reuse the same technique to bypass fraud and bot detection solutions as well. There are other projects like OpenWPM. Also, this came out of Princeton. And FP Random actually is available on GitHub. So the idea is basically what you want to do is you want to create a database of normal fingerprints. And when the JavaScript runs, instead of lying back with a random fingerprint, you can lie back with a fingerprint of your choice, right? So you can pick a fingerprint, and then when the JavaScript runs, that's the fingerprint you're going to send it to them, right? So here is, for example, here is an example. So here is a normal Safari browser, which is running. Here is a code which is derived from this fingerprint.js library. What it's doing is doing canvas fingerprinting. The details are not very important, but what it's doing is basically it's drawing on the canvas element, and it's reading back the raw pixels from the canvas element. So when you read it back, so the result is basically an image which is base64 encoded, right? So you get this long string, right? And then these scripts, they create a MD5 hash of it and then use it as a fingerprint. What I did was I got the source code of Safari of WebKit. I modified the browser. I figured out exactly where is the function called to read back from the canvas. I modified it, right? So for example, in this browser, when you run the same piece of code, which is getting the canvas fingerprint, instead of getting this long stream, it returns this fake canvas fingerprint, which I chose, right? So instead of returning this fake canvas fingerprint, I can return anything which I want, which brings me to the point of like, if I create a database of normal fingerprints, I can basically cycle through them and then basically reply back to this script. And in fact, when I was doing this research, I found like some of the bad guys are already doing this. Like there is this tool called Anti-Detect, which gets sold for $400 in the underground, right? And then it's basically a custom Firefox browser where you can customize it, and then you can customize each JavaScript property. Like on the right-hand side, if you do windows.screen, like this would be the output, right? And if you want to figure out what is the user agent, you can set it to any user agent of your choice. So the bad guys have already figured out, like these scripts work by figuring out your browser fingerprint. So they're investing a lot of time and effort on writing tools which can forge those. Interestingly, even though this tool sells for $400, it is not as sophisticated as the tool from academia, fprandom. So I guess these guys don't read academic papers. So the next thing is basically user behavior. I'll go over it really fast. So again, since I control the client side, I actually don't need to move the mouse. I don't need to press any keys. What I did was basically I had a man-in-the-middle proxy sitting in front of my browser. It would basically, when my browser would send the payload, it would append to the payload this user fingerprint, right, which is derived from a normal fingerprint which I generated. So it would generate some sort of random disturbances, randomize it a little bit, right, and it would send it back. Okay. So the next issue is that JavaScript basically cannot protect against all flows. So the idea is, of course, in this scenario, there was this user which was using a browser to authenticate to the server. What if there is a mobile app which can be used to authenticate to the server? What if the mobile app is using some other authentication flow? Like how would JavaScript be able to defend against that? In this scenario, many of the vendors, what they're trying to do is they're trying to use mobile app SDKs. So they basically recompile the mobile app. So if the banking app has their own, say, Android app, they would recompile this with an SDK, where instead of a browser fingerprint, they would have something like a device fingerprint. Again, like what is the fingerprint of your device? And they would have, the user fingerprint, and then they would send it back. But as you can imagine, again, this code actually runs on the client device, like the previous code in the client browser, which again is controlled by the attacker. So you can basically lie back. So I think, even though I've not looked at all these SDKs in detail, I think they face similar issues. The final issue is basically the mitigative action. So suppose I authenticate and I get blocked. So suppose I pick a particular browser fingerprint, I sent 100 requests. After 100 requests, I got blocked, right? So this basically gave it to me that basically now the attacker knows with this fingerprint with 100 requests, I get blocked. Let me change that, right? And given the scenario in which, for example, especially for bot detection solutions, where they are trying to detect against automated programs, so the bad guys also get a response back really fast. So very quickly, what they can do is they can figure out the blind spots of the machine learning models. Like given this fingerprint and given this for example, number of requests, I'm able to bypass them or whatever, right? So I think that's another big problem. And finally, there are a few other interesting things which I found. So first thing is basically the fraud and bot detection solutions are themselves fingerprintable. What I mean by that is, for example, if I use a particular vendor which is located at abc.com/fingerprint.js, right? So this is the magic JavaScript file. What I can do is I can I can scan the internet for the Alexa, say top 1 million websites. I can find all other websites which are loading JavaScript from the same domain, right? So now I know exactly all of the customers of that particular vendor, right? The way the attackers can use this is basically like going back to my previous attack. They can distribute their attack against these different vendors, these different websites. Like for the first site, I pick a browser fingerprint with 100 requests. I got blocked. So instead of going back to the same website, I can go to another customer of the same guys with slightly different fingerprint and so forth. Right? So you can basically distribute these attacks. Another issue is basically, as I said, people are using mobile app SDKs, but yeah, they have similar issues as well. And finally, some takeaways. Like when I started looking at many of these solutions, I found like there are many implementation and architectural issues in many of these deployments. Again, you should understand that according to the threat model, the JavaScript runs in an attacker controlled environment. So I as an attacker can see exactly what you're looking for, and I can forge exactly all the things which you are consuming. So for example, if you're a data scientist who is actually consuming these signals, you can never trust these signals because I can forge all of the signals. Another thing I should mention is, again, you should understand the limitations. These solutions work in many different scenarios, but of course, there are many scenarios in which they definitely don't work. And final thing I would say is basically you should protect all flows. Like if you have a fraud detection solution deployed for a website, you should implement it on your mobile app as well, because if you're not doing that, like you're basically closing one door and you're opening the back door, right? With that, I'll take any questions. Yeah.
And privacy issues? Are people using the exact same type of technology to track you?
People are using almost exactly the same kind of technology. So like, actually, most of the work in browser fingerprinting is actually, as I mentioned, derived from a lot of work done in privacy and preventing user tracking. Like I think even there is a browser called Brave. I think there was a talk last year at OWASP AppSec where they talked about the browser, which is basically designed to block some of these fingerprinting files. Like for example, Tor by default blocks canvas fingerprinting. And I think the new version of Firefox also has some sort of anti-fingerprinting techniques built in. Yeah, so they're actually using very similar kind of techniques.
One of the biggest challenges, as you mentioned, is that we've rolled back kind of to this client-server architecture. Mm-hmm. From that perspective, have you seen any novel techniques to protect the methods of, say, generating client-side tokens, et cetera, as you've been doing your research?
Sure. I mean, I've seen in some implementations, people put a lot of effort in protecting the JavaScript because they realized how important this particular piece of code is. So what I've seen is in some scenarios, they were using multiple layers of obfuscation, right? So they would use some obfuscation techniques. And then again, the issue is, again, everything is sent back to the client, right? So given enough time, you can actually break them. So I don't know exactly what's a good way. Again, there was a paper which came out of academia a few months ago. It was called Trust.js. And the way they proposed a solution to this kind of architecture is to run JavaScript in a browser running in Intel SGX. Right, so you can protect against any sort of tampering, but I don't know how practical that kind of solution is.
Yeah, hi there. Just curious about where you see your research going next. It seems kind of like foundational. You've done a lot of foundational work. What's your next step? Thank you.
I think a lot of the next step would be, so there's a lot of work on adversarial machine learning. Like there was some work published where people even talked about stealing machine learning models. For example, there was an attack proposed where what you could do is, there was a machine learning model implemented using an API, and what you could do is you can query a particular image, and you will get a result back that, for example, this image is a horse with this amount of confidence. I think you can launch similar kind of attacks in this scenario as well, where because like with this kind of browser fingerprint, with these number of requests, that's when I get blocked and I get a response back from the server. I think given enough time and effort, you can actually figure out exactly like what is the machine learning model, like what happens behind the scene, because that is the main piece of technology in these solutions. So I think that's one line of research. other line of research is basically looking at mobile app SDKs. Yeah, I think now we'll wrap up, and I can take questions offline.
I'm not an expert, but how does Google Authenticator and CAPTCHA-like solutions play in? Because everyone knows JavaScript is insecure, but there are other things.
Yep. Yeah, so that's a very good question. So one of the like Google reCAPTCHA, for example, also falls in this kind of scenario. But the difference between CAPTCHA system and some sort of fraud detection system is, in many of these CAPTCHA systems, you require some sort of basically the user has to, for example, solve the CAPTCHA. In bot detection solutions, the idea is, or the attacks were basically to prevent the CAPTCHA from being ever shown, right? Because if you can basically bypass the solution and then the CAPTCHA is never shown, then you basically don't have to solve the CAPTCHA. So this is the kind of the line of research I was following. But yeah, of course, as I mentioned, like these kind of attacks, of course, they don't work in all scenarios, but across many scenarios, they do work. Yeah.
Actually, we do not have time for any more questions. Can you just catch him up later?
Yeah, I'll be
just
around, so you can find me, and I'll be happy to answer
Perfect.
questions. Thank you.